Chapter 13 is about solutions, and I'm bringing us back to this diagram that we had way back at the beginning of the class in Chapter 3, because solutions are just one particular type of mixture. So remember, mixtures have multiple substances combined together in the same container, and a homogeneous mixture is one where it was all completely mixed up. Heterogeneous had different parts to it. Okay? So a solution is just the same thing as a homogeneous mixture, one that's all completely mixed up. So we'll just refer to them as solutions from here on out, but that's what it is. It's just a mixture of things that's all completely mixed up, has an even consistency. Now, in order for a solution to form, it's very important that the process of dissolving must actually occur. It's easy for us to think about just mixing things together in a container, like if you had two different types of powder, you could pour them in a container and stir them up, but that's not a solution because a solution requires this dissolving process. And what dissolving is just mixing at the molecular level. Meaning the molecules themselves are interspersed between each other. So remember, we haven't actually changed any molecules. It's still just a physical change. But to have it really completely mixed up, you have to have molecules of the solute interspersed right between molecules of the solvent. So an example is solid sodium chloride. If we mix it with water and just stir it up, we end up with NaCl, now with an AQ phase label because it's been dissolved in water. That's just the formation of salt water, but the solid dissolves in the liquid to make this solution. So let's just get our terminology straight here. Every solution has one solvent. It's just the major component. Of the solution. Okay, it's just whatever we have more of. The solute or solutes are just the minor components. There can be more than one solute. There can be several things dissolved in the solution, but there's always only one solvent. So, for example, just regular tap water, H2O, is the solvent, but there are lots of solutes. There are a lot of ions floating around. There's some dissolved oxygen. There's fluoride, if your water system puts that in it, and so on. One little rule of thumb, though, is that the solvent is the liquid if we're dissolving a solid. The liquid is the solvent. Let's just write that there. There are some rare cases where we could actually have more of the solid than the liquid, but it's still the liquid is considered the solvent. So that means that in NaCl-AQ, water is always going to be the solvent. NaCl is always going to be the solute. The solvent dissolves the solute. Okay? Water is dissolving the NaCl. The solute is being dissolved by the solvent. So just make sure you get that kind of terminology correct, and together they make a solution. Okay, so these are the components of the solution. Let's just take a second here and familiarize ourselves with the different ways that a solution can form, and it's important that at least one of the fluid phases, right? Liquids are fluids, but gases are fluids also. Remember in chapter 12, we talked about how the fluid phases are the ones where the molecules are actually moving relative to each other. So that fast molecular motion has to be happening in order to get that mixing at the molecular level that we need in order for a solution to form. So the most common way we think of a solution forming is a soluble solid. Okay? The solid has to be soluble. Not all solids dissolve in all liquids, and we'll talk about that a little more in just a second. But as long as the solid is soluble in that particular liquid, we form a solution that looks like a liquid. We really only use the L phase label for pure liquids, but we have a liquid solution. I mean, it looks like a liquid. You can pour it out. The specific phase label, though, depends on what solvent you used. AQ is our phase label if H2O is the solvent. Okay. So liquids and liquids can mix together to make a liquid solution, but only if the liquids are miscible. M-I-S-C-I-B-L-E. We talked about that in the last chapter also, where if we have liquids that mix together, we call them miscible. Water and ethanol, one of the alcohols, are miscible. So you can make a mixture of water and ethanol at any proportion. You could have 5% ethanol or 50 or 80 or 90%, and it'll all mix together and make a nice solution. Not all liquids are miscible, and we'll talk about that more on the next page. Gases are able to dissolve in liquids, again, making a liquid solution. Things like oxygen that's dissolved in water. You know, that's how fish can breathe underwater. Their gills are able to filter out the dissolved oxygen. If you've got some Mountain Dew or Coke sitting in front of you right now, that is carbon dioxide that's been dissolved in water to make it carbonated that way. So the interesting thing about gases mixing together is that we make a gaseous solution, but that is for all gases. Remember when we had the picture of gases up from the last chapter, the molecules are spread way far apart from each other, so they really have little to no interaction with their neighboring gas molecules. So a gas molecule is flying around pretty much independent of the other gas molecules. So it really doesn't care if those are other molecules like itself or other molecules of different gases. One gas will just spread out to fill its container, as well as some other gas will also spread out to fill that same container, and eventually they'll just be evenly mixed together. The way that solids can form a solution is maybe not quite what you think. Remember I said that you could imagine just having two powders and you could even grind them up and get it so that it looks like it's mixed, but we've not formed a solution unless actually dissolving has happened, and that's why one of these fluid phases must be present. So there's no way that two solids just together in a container can make a solution, right? Remember, the molecules in a solid are just locked in their own structure, right? They may even be vibrating in place, but they're not going to mix with a different solid that has its own structure. So what we have to do is actually heat it up until both of the solids, or at least one of the solids, melt. And then we can mix them together and get a molten liquid solution. Because now we have liquids, we have one of those fluid phases. We can get mixing to happen at the molecular level, but then by cooling it down, that's how we can get a solid solution. And an alloy is a solid solution of metals that's made in that way. So, for example, brass is an alloy of copper and zinc. If you heat them up and get them molten, you can mix them together, and then it'll re-solidify again into something with an even consistency, okay? But it's still just a mixture of those two metals. Remember, in a metallic solid, like either copper or zinc, all the atoms are just stacked together, So when we have an alloy, we'll now have a mixture of those copper and zinc atoms just all stacked together in random order. It's different from an ionic solid where you've got plus minus plus minus plus minus plus minus like that. Here, the solids will just all be stacked together but in random order. Let's talk a bit more about how it is that two liquids can mix together, or even what it is that determines whether or not one thing will mix with another thing. And it comes from like dissolves like. Polar substances will dissolve other polar substances, and nonpolar substances will dissolve other nonpolar substances, but we have trouble trying to get something polar to dissolve in something nonpolar. So common polar solvents, things like water, right, that we're very familiar with, methanol here. Both of these are polar because they have hydrogen bonding, right? Acetone, here's its structure, still polar, not hydrogen bonding, okay? So it's not as polar, but sometimes when it's a little less polar, it makes an even better solvent because it can start to also dissolve things that are not quite as polar too. Okay? But in each case, all of these polar solvents tend to dissolve polar solutes, and we'll talk more about this in a second, soluble ionic compounds. We'll talk about why that is in a moment. But an ionic compound, if it's soluble, it will require a polar solvent in order to dissolve. Now, nonpolar solvents that are common, things like hexane. Remember, that's just 6 carbons all in a row. This is toluene. Nonpolar again, because they're both hydrocarbons, and hydrocarbons are nonpolar. This is carbon tetrachloride. It's a carbon with 4 chlorines pulling equally out from that carbon, so it's nonpolar also. Carbon tetrachloride used to be the solvent used in dry cleaning. It's nonpolar. It dissolves other nonpolar solutes, like oils and greases and dirts and things that make clothing messy, so it works really well for dry cleaning because it rinses all the dirty stuff away, and then it can be evaporated very easily. Okay? And it was used a long time for dry cleaning until all the dry cleaners started getting cancer. They found out that carbon tetrachloride is a terrible carcinogen. Okay? It causes cancer very badly. So now a lot of times what they use in its place is actually a very similar molecule, but just instead of one carbon in the middle, oops, that has to be a chlorine too. It's a CC double bond, tetrachloroethylene, but also nonpolar because you got 4 chlorines pulling out equally in 4 equal directions like that. Let's write that tetrachloroethylene, but still nonpolar. So that's right now what's very commonly used for dry cleaning purposes. So polar things dissolve polar solutes, nonpolar things dissolve other nonpolar things. Paint thinner is a mixture of a lot of different hydrocarbons, but it's nonpolar. It dissolves nonpolar oil paints. Latex paints are water soluble. Latex paints are made out of polar substances, so they dissolve in water. So let's pretend that we have only 2 solvents to pick from, either water or hexane. Water being polar, hexane being nonpolar. We can then pick which of those 2 solvents each of these would more easily dissolve in. So ethanol is an alcohol. It has hydrogen bonding, which makes it polar. So it's going to dissolve well in the polar solvent. Dissolves in water. Okay. So if we had our choice, water would work better at dissolving it. Now CBr4 is tetrahedral, might as well draw it. Oops. Br, Br, Br. We've got 4 bromines all pulling electrons away from the center, but doing so equally, making the molecule nonpolar, so it'll dissolve in hexane, the nonpolar solvent. I2 is a nonpolar molecule, right? Those 2 electrons are shared equally between the I and the other I there, so hexane will dissolve it. Pure iodine is a purple solid, and it's very insoluble in water, right? You put the little crystals in water, they'll just float down to the bottom and do nothing, but if you dropped it in hexane, they would dissolve almost instantly before they even got to the bottom. CuCl2 is different from all these ones above it, right? Can you see why? Look at these elements, copper and chlorine. Copper is different. Copper is a metal. These ones are made out of only nonmetals. So CuCl2 is made out of copper 2+ ions. It's made out of chloride ions. It is an ionic compound. And I told you up here that polar solvents can dissolve soluble ionic compounds. So it has to be soluble, but we would definitely have a better chance in water. There's no chance that an ionic compound can dissolve in a nonpolar solvent like hexane. Okay, so H2O would dissolve it if anything would. Be careful with NH4Cl because it looks like it's molecular, right? It's all nonmetals, but you have to recognize that NH4+ is a polyatomic ion along with chloride, so it is also ionic and would dissolve in water, if anything. Okay, so be on the lookout for polyatomic ions like NH4+, the ammonium ion. I told you up above that greases and oils and things like that dissolve. The greases and oils are all non-polar, right? So that's why they dissolve in hexane. That's why dry cleaning uses a non-polar solvent, pretty much. So you should be able to, if you're given a compound on an exam or something like that, you should be able to say whether it is polar or non-polar, which of the solvents it would be more likely to dissolve in, the polar solvent or the non-polar. You know, I could ask that question, which of these would dissolve in water? Would this substance better dissolve in water or hexane? Anything like that. Now, I had told you that in order for an ionic compound to dissolve, it has to be in a polar solvent. And the key to understanding that is that when an ionic compound dissolves, its ions separate from each other. Here is a solid ionic compound like NaCl. When we put it in water and stir it up, it dissolves, but in order to do that, its ions have to break apart from this ionic lattice. So we have separate positive and negative ions floating around in that solution, right? The little ones are the plus, the big ones are the minus. So that's very important to understand, okay? That those different ions have to separate from each other. So a solution of a dissolved ionic compound has the separate positive and negative ions floating around independently in the solution. Okay? In the pure solid, the positive and negative ions are stacked together in this ionic lattice. The reason for that, let's zoom in here. Here's our solid again. Here we have water molecules approaching the solid, and look at the direction that this water molecule is approaching that Cl- ion. Remember, an H2O molecule has a partial negative on the oxygen, partial positives on the hydrogen due to the electronegativities in there. it's the partial positive hydrogens that are attracted to the negative ions on the surface of that ionic solid. And likewise here, the partial negative side of the molecule is attracted to the positive ions on the surface. Okay? And if enough water molecules get around one of these ions on the surface, it can actually remove it from the rest of the solid. And then these water molecules surround the ion. H2O molecules surround the ions, the individual ions. And that only works because if we have a minus ion, all the partial positive sides of the water molecules are attracted to that, and they end up totally surrounding that ion. Here is a Na plus. All the partial negative sides are attracted to that, and it surrounds it that way. But that requires a polar solvent. Nonpolar solvents can't do this because nonpolar solvents don't have that permanent negative and positive ends to it. Okay? So the ions have to get surrounded by solvent molecules, and then this whole aggregate can be floating around in the solution then. Okay? This ion is perfectly stable now that it is surrounded by those opposite charges. But the thing is, that only happens if the ionic compound is soluble. If I write the formula of an insoluble compound like calcium carbonate, that's like chalk dust. If you poured that in water and stirred it up, it would just remain in its solid ionic lattice. Because, look at the ions, calcium 2 plus, carbonate 2 minus, in comparison to Na plus and Cl minus, look at these larger charges. Those larger charges mean that the ions are more strongly attracted to each other in the solid. They have stronger ionic bonds. The water molecules can only approach and remove ions from the surface if those ionic bonds aren't too strong. Here in NaCl, we only have single charges holding those ions together, so water molecules can surround and remove them. Okay? Here we have those larger charges, and the way it works, this is actually 4 times stronger attraction than just plus and minus. Okay? If just one of these was 2 plus, it would be twice as strong. But if they're both 2 plus, it's actually 4 times as strong. So these ions are held very strongly together. The water molecules cannot remove them from the surface, so it just remains in that solid ionic lattice, even if it happens to have water molecules in the same container. It only dissolves if the water molecules can remove those ions. So if you get a chance, look back at the solubility rules from chapter 7, which we used to predict whether or not a substance would dissolve. The insoluble compounds, like this one, tend to have the larger charges, okay, because that attracts those ions more strongly together. The soluble compounds tend to have smaller charges, which means that water is more able to remove them from the surface and then ultimately surround them in the solution that way. But even before, we tended to think about solubility as an absolute thing, right? In other words, we liked to think of if something dissolves, it totally dissolves. If something does not dissolve, it doesn't dissolve at all. But even if a compound is soluble, there's a limit as to how much solute will dissolve. Okay? It would be really weird if you had 100 milliliters of water and then you just started pouring salt in it and you could just keep pouring salt in it forever, right? It would never work, of course, if you tried to pour tons and tons of salt into that container. Obviously, there has to be some limit as to how much can be dissolved. So that's called the solubility level. Okay? And it turns out the solubility of sodium chloride is 36 grams will dissolve per 100 milliliters of water. That's typically how solubilities are given. If you have 100 milliliters of water, how many grams of the solid will actually dissolve? And if we had actually 36 grams dissolved in that 100, we'd call that a saturated solution. It's a solution that's currently holding the maximum amount of solute. And you can always identify a saturated solution if it has undissolved solid sitting at the bottom of it. Okay? That's the way you actually get a saturated solution. You pour way more than 36 grams into 100 milliliters. Only the 36 will dissolve, and the rest of it will just be sitting on the bottom. But that's the way that you can be assured that you have the maximum amount that's dissolved. Okay? You just pour the liquid off the top, and that's the saturated solution. An unsaturated solution is one that holds less than the max. Okay? So if we only had a little bit of NaCl in the solution, we could add more solute to an unsaturated solution and it would dissolve. Now we'll talk about this more in a second, but a supersaturated solution is one that we've convinced to temporarily hold more than the maximum in solution. Okay? So if we were able to actually get dissolved more than 36 grams, that's supersaturated, and I'll tell you in a second how that would come about. But right now, let's look at these examples, and here's sodium chloride's solubility. We can figure out how we'd classify each of these. So say we had 15 grams dissolved in 100 milliliters of water. How would you classify that if the solubility is 36 grams? Well, it's unsaturated because we've only got 15 out of the possible 36 that could be dissolved. We could pour more into this and it would dissolve. Now here, what if I had 100 mils of water, I poured 50 grams of salt into there, okay, and stir it up for a while. There's undissolved solid sitting on the bottom. That was pretty much the definition I used of a saturated solution, because even though we poured 50 grams in there, only 36 will have dissolved. Okay? The rest of it, the remaining 14 grams, would be sitting as solid on the bottom of the container. Right? But if we took a little bit of the liquid off the top, we could be assured that that is a saturated solution. What if, by some means, we were able to actually get 38 grams of salt to be actually completely dissolved in 100 milliliters of water? Well, since the normal solubility is just 36, that's actually a supersaturated solution. And how would you do that? Well, the key here is that solubility often changes with temperature. If we heated up that water, those molecules are moving faster and they're more effective usually at surrounding the ions in the solution. So what if we take some really hot water and dissolve salt in it? We would be able to get more than 36 grams. This would probably just be the room temperature solubility. So we get a solution loaded up with more than 36 grams at a real high temperature, get it all dissolved, and then slowly and carefully cool it back down to room temperature. If we do it slowly, that extra solid will remain dissolved. It won't just immediately come out the second that the solubility level is reached, because that extra solid has to have some place to form. Okay? If we made sure our container was clean and we make sure no dust falls into it or anything, that extra solid won't have anywhere to form, so it has no choice but to remain in solution, but in sort of an unstable state. So what's really neat then is that if we have a supersaturated solution, this one is a supersaturated solution of sodium acetate. And sodium acetate is kind of special because the solubility is really different when it's hot than when it's cold. You can hold 3 or 4 times as much when it's hot as when it's cold even. I think it's that much. Might not be quite that much, but there's a huge solubility difference. So we heated this up, we dissolved a whole bunch of solid and slowly cooled it down. then all we need is to just touch the surface with something that's abnormal, like in this case, a glass stirring rod. What'll start to happen is that now that extra solid that's just sitting in there waiting to crystallize will immediately start to crystallize right at that point where we introduced the irregularity. And these crystals will grow outwards, right, very quickly in a matter of seconds. And they're sort of needle-like crystals. And what happened here, something probably fell down to the bottom, and crystals started to grow from the bottom. And very soon, there'll be solid crystals sort of overtaking this entire thing. So now the solution is just saturated because we've removed all that extra solid that doesn't really belong there at that particular temperature, although we could heat this back up again and get it to dissolve and do the same sort of thing over again.